For decades, accessible architecture has been treated as a medical afterthought. It is typically visualized as a series of sterile, clinical add-ons awkwardly bolted onto a finished room to satisfy a building code. But an optimal physical environment remains neutral regardless of a user's biomechanics. Building a truly inclusive space requires an engineering rigor that extends far beyond the basic installation of wider doors or concrete ramps. This process is known as parametric optimization. A universally designed room operates as a calibrated matrix, mathematically calculated to accommodate the full statistical distribution of human interaction. To understand this system, we have to look past the aesthetic surfaces of a room and map the invisible physical forces governing human movement. Optimizing these forces requires architects to master two distinct variables: kinematics, the geometry of motion, and photometrics, the measurement of light. Treating accessibility as a post-construction checklist causes a space to fail its users. True inclusivity is engineered into the foundational mathematics of the floor plan. The first test of a space's kinematics occurs at its primary threshold, the doorway. Negotiating this threshold requires adherence to a rigid spatial parameter. For manual and power mobility devices, that parameter is the standard wheelchair turning radius. A 60-inch minimum turning circle intersects common door swings. A standard 32-inch door clashes with this sweeping radius, forcing reverse maneuvers to enter. Establishing a 60-inch metric at every pivot point provides kinematic freedom. Without it, the room becomes a physical trap. Once the macro spatial layout is resolved, optimization scales down to the micro interaction point, the door hardware. Operating a traditional round knob requires tight, sustained grip strength combined with a simultaneous twisting rotation of the wrist. A lever handle functions through a single downward push. The mechanical advantage of the lever determines its accessibility. This vector diagram compares the forces. The round knob demands high rotational torque. The lever converts a minimal downward linear force, applied by an elbow or closed fist, into the rotational energy to retract the latch. This mechanical advantage removes physical barriers for users with limited dexterity. Kinematic accessibility succeeds by mathematically minimizing physical friction across every user interaction. Moving past the doorway, the physics shift from upper body mechanics to lower body locomotive physics. The flooring surface dictates the locomotive stability of every person walking, rolling, or using a mobility aid in the space. The crucial engineering metric here is the static friction coefficient, which measures the resistance between a shoe or tire and the floor. This graph plots slip probability against static friction coefficients. As the coefficient drops, slip probability spikes. Safety is achieved when the coefficient reaches 0.6. Engineered non-slip flooring materials are designed to maintain this exact target friction coefficient, even when subjected to moisture. That same friction is applied against gravity during vertical traversal. Traditional stairs demand intense bursts of vertical lift, while ramps distribute that required energy over horizontal distance. The universal architectural standard for unassisted accessible ascent is the 1:12 slope gradient ratio. In this cross-section, we see the 1:12 ratio. For 1 unit of vertical rise, there are 12 units of horizontal run. An overlaid vector illustrates the reduction in peak kinetic energy. This specific slope ensures manageable pacing, allowing unassisted ascent without triggering rapid muscular fatigue. Gravity and friction are constants. A universally designed space manipulates floor geometry to equalize the locomotive effort required by users of all physical abilities. Physical kinematics solve only half of the environmental equation. The remaining challenge lies in the complexities of sensory processing. Universal lighting design is a mathematically rigorous component of spatial accessibility. Direct glare and harsh shadowing obscure depth and create false obstacles. Designers eliminate these hazards by implementing soft, diffuse lighting that washes out sharp contrast. Direct glare demands constant pupil dilation and contraction. In aging eyes, this causes immediate sensory overload, disorientation, and visual fatigue. Architects solve this by implementing multi-layered ambient lighting schemes that distribute illumination evenly across all surfaces. This even distribution is critical for spatial orientation, specifically for visually impaired users attempting to navigate an unfamiliar room. When high-fidelity details are unavailable, the brain relies on detecting the gross geometric boundaries of a room, the intersection where the floor ends and the wall begins. The critical metric for establishing these boundaries is the light reflectance value, or LRV. LRV is the precise percentage of light that a given surface reflects back into the space. This false color luminance map illustrates how manipulating LRV creates a sensory map. By calculating the exact difference in reflectance between the horizontal floor plane and the vertical wall plane, designers can guarantee a visible edge. Maintaining a minimum of 30 points of LRV contrast at this intersection allows users with severe visual impairments to safely detect the physical limits of the room. Universally accessible lighting provides a legible photometric map, allowing the user's brain to decode the physical geometry of the architecture. There is a prevailing industry misconception that integrating accessible design compromises luxury aesthetics. This perceived conflict stems from post hoc design practices. It is a failure of planning, not a mechanical limitation. When executed correctly from the ground up, parametric optimization blends into the architecture. Wide clearances, subtle gradients, and diffuse luminance align with modern, spacious design. At the highest level of execution, high-end interior architecture and universally accessible design are synonymous. A space operates at its maximum functional capacity when physical, locomotive, and sensory friction is reduced to zero for every user. Universal design represents a standard of architectural rigor where the success of a space is measured by its capacity to serve the full spectrum of human movement.